Hello everyone, we are from Group 14 and our topic for the assignment is digoxins and this is our group members. First, my name is NURIN and I will introduce about the applications of the digoxins. There are many applications of the digoxin. One of it is it was used for the treatment of the mild to moderate the heart failures in adult patients, and it will increase the myocardial contractions in children together with the heart failures. For example, in the heart failure cases, the digoxin help to strengthen your heart contractions and improve the blood flow in your body. So the digoxin is used along with the other medications to treat the heart failure, which is a condition that will result in the heart not pumping as well as it should. So by the application and we eat the digoxin pills, the digoxin it will works by slowing down your heart rate and making your heart beat more strongly, which make it easier for your heart to pump the blood around your body. And next is application of the digoxin is to use in the treatment of cardiac arrhythmia and atrial flutter. Besides that, it will also use to control a ventricular rate in the adult patient diagnosed with the chronic atrial fibrillations. Next is digoxin is used for the treatment of the fetal supraventricular tachycardias, and it will also reserve as a backup drug when the first-line agents are ineffective. Next is it will use in treating vital infection, inflammatory cancers, hypertension, and neurodegenerative disease. We're going to see about the two mechanisms of action of digoxin. First, digoxin will act as a positive ionotropics. So if you can see from this diagram, first is the digoxin, it will inhibit the Na/K ATPase enzyme and it will result in the reductions of the intracellular potassiums. And this, it will increase in the intracellular sodium through decrease the calcium explosions within the sodium-calcium cation exchanges. So, if we can see here that this it will drift an influx of a calcium into the heart and cause an increase in contractility, which is called as a inotropics. And the cardiac output it will increase with a subsequent decrease in ventricular filling pressure. So if we can see from the picture here, we can see that when the sodium cation it insert into the cell membrane, we call it as a prezeros, and when the calcium cation it insert into the membrane, we call it as a press-2, and when the kalium, which is K plus ion, it will up in the cell, we call it as a press-3. So the next is the digoxin will act as the AV node inhibition. As we can see here, the rise in the calcium level will lead to the prolongations of the press-4 and press-0 that we just talking about, and it will increase the node refractory period. So it will result in slower the conduction through the AV node and a decrease of ventricular response.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad ARIFF ISKANDAR bin KHAIRUL BAKHTIAR. My metric number is S67337. On the previous video, my friend already explained about the introduction of digoxin. So in my part, I would like to explain the class of compound, building block and chemical structure of the digoxin. Let's take a look at the chemical structure of the digoxin. The chemical structure of digoxin consists of steroid nucleus, lactone ring and a sugar moiety. On the steroid nucleus, there is a 4-ring system, 3 cyclohexane rings and 1 cyclopentane ring. On the lactone ring, it is connected to C17. On the other hand, on the sugar moiety, it is attached to C3 in some cases. You guys might be wondering, what is the class of compound for the digoxin? The class of compound for the digoxin is a cardiac glycoside. What is the cardiac glycoside? It is a secondary metabolite commonly distributed in plants such as Digitalis purpurea and Digitalis lanata. The cardiac glycoside is useful in treating heart failure and arrhythmias due to their ability to enhance cardiac contractility. Instead of digoxin, another class of compound that consists of cardiac glycoside is owabin, strofantin, bufalin and oleandrin. Recent study shows that there are a lot of applications regarding cardiac glycosides. For example, cardiac glycoside serve as antiviral against virus such as influenza, COVID-19 and so on. It is proof that cardiac glycoside have anti-cancer properties, which inhibits the sodium-potassium, disrupting ion homeostasis within cancer cells to kill cancer cells. Moreover, the function of cardiac glycoside is to treat heart failure and improve cardiac output in people who have a heart failure. The last part of the digoxin is a building block. So the digoxin is made up of the digitoxygenin. And what is the digitoxygenin? It is a steroidal glycone serving as the core structure for many cardiac glycosides, including digoxin. On the other hand, the digitoxygenine can serve as a glycone or sugar-free portion of cardiac glycoside like digoxin. The glycones of cardiac glycoside can be divided into two main groups, which is cardinolite and bufadienolites. We can see these two groups on the structure of the digoxin.
Alright, for the next part, I will tell about the biosynthetic pathway for digoxin that includes a synthesis and mechanism that we have learned in natural product chemistry. So we have three parts for digoxin biosynthetic pathway before we get our final product, which is digoxin drugs. For the first one, which is a MVA pathway to form a squalene. So it shows the first pathway on how the digoxin pathway starts. Begin with MVA synthesis. Next, the second one is a synthesis of squalene to form a cycloartenol, which we will show some mechanism and synthesis for squalene to form an exact cycloartenol compound. And the last one is a final digoxin pathway that shows the last synthesis and biosynthetic pathway for forming digoxin drug compound. So for MVA pathway, we will have two parts, which is part 1 and part 2, where the part 1 we will tell about how it starts from acetyl-CoA compound to form IPP product. So this is the figure that shows the synthesis of MVA pathway to form squalene, and the upper right in this slide is a MVA, or its full name is mevalonate acid. So the first step of the pathway starts with acetyl-CoA compound, which is a 2-carbon molecule derived from the breakdown of carbohydrates, fats, and proteins. Then these two acetyl-CoA compound will come together to form aceto-acetyl-CoA compound. Secondly, a third acetyl-CoA compound or molecule will condense with aceto-acetyl-CoA to form a HMG-CoA compound, or its scientific name, which is 3-hydroxy-3-methylglutaryl-CoA. As you can see on the slide, it used a mevalonyl phosphate or MVA, and it did not use a HMG-CoA compound. Because why? Although HMG-CoA and MVA are not the same compound, but they are both molecules involved in the mevalonate, which is in this MVA pathway, but at different stages. So the later steps in the MVA pathway shows the convert of HMG-CoA or MVA to isopentenyl diphosphate, which is IPP, and dimethyl allyl diphosphate, which is DMAPP. Then a similar pathway we used to synthesis squalene. The overall biosynthesis of the synthesis squalene from MVA is summarized in this first part of this MVA pathway. So we already know the first part that form an IPP compound. And next, for the second part of this MVA pathway, it will shows how an IPP compound will synthesis to form a squalene product. Alright, firstly, HMG-CoA is reduced by HMG-CoA reductase to mevalonate with the input of two ATP molecules. So this reaction is considered as a rate limiting step in the MVA pathway that we have learned in physical chemistry. So this mevalonate is phosphorylated by mevalonate kinase using ATP to form mevalonate 5-phosphate. Then this mevalonate 5-phosphate is further phosphorylated by mevalonate kinase with ATP to form a mevalonate 5-pyrophosphate. And this mevalonate 5-pyrophosphate decarboxylase converts a mevalonate 5-pyrophosphate into isopentenyl ferrophosphate or IPP with the release of phosphate and carbon dioxide. For the next one, IPP will isomerize to dimethyl allyl pyrophosphate, which is DMAPP, where IPP and DMAPP are the building blocks for squalene synthesis. For the next one, we will use a knowledge that we have learned in the last semester, which is carbonyl compound, where these two IPP molecules will combine together to form a geranyl pyrophosphate, which is GPP, and then it will synthesize with itself to form a DMAPP molecule and also form a farnesyl pyrophosphate, which is FPP, through the enzyme farnesyl pyrophosphate synthase. So this is a mechanism for IPP and MAPP to form a squalene product. So this is an arrow that shows how the hydride and carbon shift happens in this mechanism. Finally, squalene synthase will condense these two FPP molecules to form a squalene, the final product that shows in this figure. Okay, the next one is a synthesis of squalene to form a cyclooctanoyl compound. So this squalene epoxidase is an enzyme with FAD, which is flavin adenine dinucleotide, will bound as a cofactor. So this squalene, which is a substrate, will bind to the enzyme. Oxygen is consumed in the reaction, and ADPH will donate an electron to FAD and reducing it to FADH2. Then the reduced FADH2 will abstract a hydrogen atom from a specific carbon atom on squalene, and it will form a new carbon-oxygen bond, which is epoxide, and converting the squalene to 3s-2,3-oxidosqualene as shown in this figure. So from the latter slide, we can make a synthesis from squalene to cyclooctanol. So the cyclization of 2,3-oxidosqualene into cyclooctanol by cyclooctanol synthase, which is an enzyme. This conversion is a key step in the biosynthesis of sterols and digoxin in the plants. So cyclooctanol synthase is an enzyme that uses 2,3-oxidosqualene as a substrate. So this stereochemistry of the product, which is cyclooctanol, is determined by the enzyme and the mechanism on how cyclooctanol is synthesized from oxidosqualene is shown in this figure. So this is the last part of digoxin pathway. So we have formed a squalene, and then we have formed a cyclooctanol compound. So this is the full digoxin pathway that shows from the first slide until now. So the digoxin pathway will produce several intermediates before ending with digoxin. There are some steps that involve in the digoxin pathway where cyclooctanol is converted to 24-methylene cyclooctanol by assembly 2. Then 24-methylene cyclooctanol is converted to a diol intermediate by an unknown enzyme. So the diol intermediate is converted to 24-ethylene lophenol by SSR1, and the overall pathway of synthesis of digoxin is shown in this figure.
So next, let's take a look to synthesize in laboratory of digoxin compound. Digoxin compound started from using compound 4 as starting material, which is digotoxyl orthoalkyl benzoate. Donor 2 was prepared to start the synthetic research by removing the benzoyl group and then acylating with 2,2-dimethyl-2-orthonitrophenylacetone anhydride DMNPAA under the influence of trimethylsilyl trifluoromethane sulfonate as act as catalyst to produce compound 5. So the second DMNPA group was introduced on compound 4, which is digotoxyl orthoalkyl benzoate. 3,O,2,2-dimethyl-2-orthonitrophenylacetal was observed during the selective cleavage of 4-O-benzoyl under basic condition. This is due to the cis-vicinal interaction between 3,4-hydroxy of digotoxos. However, after acylation with DMNPAA, both regioisomers produce the same product, which is compound 5, suggesting that the migration of the DMNPA group was not significant. To obtain beta-2 solely, methyl glycoside compound 5 had been hydrolyzed and then dehydrative isolation with ABZOH under normal condition. Next, with the donor 2 was prepared by using a linear technique was to be used to include the trisaccharide sugar change. Fortunately, the influence of catalyst PH3PAUOTF, the donor 2 and digoxygenin, which is compound 3, produce the formation of monosaccharide glycoside, which is compound 6. Compound 6 is an alpha-beta mixture with the ethynyl beta isomer as main product. After that, due to the effect, zinc or cupron sulfate or acetic acid cause the 2 DMNPA groups in compound 6 produce compound 7 nearly in just 30 minutes without affecting the butanolide moiety of the glycan or acetoxin. Via a sequence of 3,4 orthoester formation and ensuring acid-mediated, the radioselective opening of the resulting orthoester, which is intermediate 7, which is hydrogen, was inserted to selective discrimination of the acyl 3-hydroxy with an acetyl group, forming compound 8. Compound 8, which was all set for sugar chain extension via 4-hydroxy. So for the next step in the sugar chain extension was coupling of compound 8 with donor 2, which is done at 0 temperature with the presence of acid wash to guarantee good yield and high stereoselectivity of compound 9. The effect of vicinal electron withdrawing acetyl groups deactivating resulted in lowering the reactivity of acceptor 8 compared to compound 3. Compound 3 led to a small modification of normal glycosylation condition. In order to produce compound 10, the deprotection of the 2 DMNPA groups in compound 9 was formed, maintaining the butanolide moiety and 2,3,12-O-acetyl groups intake. Only take 30 minutes, modify compound 7 into compound 8, produce acceptor 11, which was ready for the last digitoxyl residue to be added. Thus, the condensation between compound 11 and donor 2 proceeded without incident at the slightly altered circumstances. Produce just compound 12. So then, digoxin for 2 sequence step was finally obtained by global deprotection of compound 12 through sequential removal of DMNPA groups and cleavage of acetyl groups. In summary, the first complete synthesis of digoxin was carried out using a longest linear sequence LLS of 9 stages, counting from the readily available digoxosyl donor 2. Thank you.